let's do an example problem here. We were going to use tabulated standard electrode potentials to calculate the standard cell potential for the reaction that's shown right there. So this equation is balanced as written. So what we're going to be trying to figure out is E cell. What is the standard cell potential? And based on what we saw in the last video, we know that the standard cell potential is equal to the standard reduction potential of the cathode minus the standard reduction potential of the anode, which probably from this point forward I will just write as cathode minus anode. So we need to figure out what is being oxidized, what is being reduced, so we know what is our cathode and what is our anode. And so if we look at what's happening here, we have two, it's a little bit confusing with this one because it looks like there's three different things happening, but there's really only two. So one of those here is we have aluminum turning into aluminum 3+. That is obviously redox happening because we have aluminum, which would have an oxidation number of 0, and it is turning into aluminum 3+, which would have an oxidation number of +3. So we have oxidation, in this case, happening. And so we can go ahead and go look for that on the table. Again, because this is oxidation, this is our anode. And its standard reduction potential is going to be, let's see here, it'll be somewhere down here, I believe. There it is. So we have aluminum 3+ and aluminum. And by the way, we do not care that it is written backwards compared to what's in the actual reaction. That's perfectly fine. It is supposed to be written backwards because here on this table it's written as a reduction, but in the reaction that we are doing, it is being oxidized, and that's perfectly fine. You're expecting one of your half reactions to be this way. One of your half reactions should be flipped opposite of the way it's written here. It's perfectly fine. We can still use this number without changing it. We do not have to change the sign on this. We will use it just as it is. We've already taken that into account with our equation. Okay, so there's the aluminum. The other thing that's happening in this reaction is we have some nitrate and H+ turning into nitrogen monoxide and water. So let's go back there and look at this and see if we can find that happening somewhere. So you're just going to kind of peruse through here and look for something that looks similar. And if I remember correctly, it's somewhere in here. Oh, there it is. Nitrate, 4 H+, going to nitrogen monoxide. And so there is our standard reduction potential for our cathode. And so that was positive 9.6. And actually, I forgot to write the other one down, I think. So we had negative 1.66 and then 0.96. Actually, that was 1.66, wasn't it? So negative 1.66. And then the other one was positive 0.96. Just double check that just to be sure. My memory doesn't always work so well. 0.96, negative 1.66. Yep, okay. And so this was our cathode here. So to find the standard cell potential, we are just going to say E cell under standard conditions is cathode, 0.96 volts, minus anode, negative 1.66 volts. So these are actually going to add together because we're subtracting a negative value. And if I plug that into my calculator, don't trust myself to do that in my head, not this late at night anyway, 0.96 plus 1.66, that is 2.62 volts. So that is pretty decently positive. That is a pretty good cell voltage for a single cell. Most people don't realize it, but like your 9-volt batteries that you have that power some stuff in your house, like your smoke detectors, for example, that 9-volt battery is not a single cell. It's actually, I believe, 6 cells, all in series? I forget the correct way to line them up, but they're either in series or parallel, whichever direction adds their voltages together. So it's actually, do not cut open your 9-volt battery to check this out, but inside of your 9-volt battery there are actually 6, I believe, AAAs soldered together to give you a single cell with a 9-volt 9-volt potential. And each of those individual AAAs inside of there have 1.5 volts. So that's pretty good. That's a pretty high voltage for a single cell. And that is a spontaneous process because it is positive. Alright, so if we're given an option, if we're just said, hey, here's 2 different half reactions, which one would you pick to be your oxidation and which one would you pick to be your reduction? Given that your goal is for the reaction to be spontaneous, you should always be picking your anode to be lower on the table. You want your anode lower and your cathode higher on the table. That will always give you a positive cell voltage if you do that, which will give you a spontaneous reaction. And by the way, going back here, you do not have to have your cathode up above the standard hydrogen electrode and your anode below. You could have your cathode here and your anode here. And that will most definitely be spontaneous. All you need is the anode to be lower. Just in some amount lower. It does not have to be way down on the table or anything like that. It just needs to be lower than the cathode, and you will have a spontaneous cell. Okay, so with that in mind here, this question is asking us, without calculating the standard cell potential, so no numbers here, predict whether each of the following redox reactions is spontaneous. If the reaction is spontaneous as written, make a sketch of the electrochemical cell in which the reaction could occur, and if the reaction is not spontaneous, write an equation for the spontaneous direction, which would just be the opposite direction. And sketch the electrochemical cell in which the spontaneous reaction would occur. In your sketches, make sure to label the anode, which should be on the left, and the cathode, and the direction of electron flow. Alright, so let's work through this. If you want to try and do this on your own, feel free. If not, we can just work through it together here. So, part A, we have iron plus magnesium 2 plus going to iron 2 plus and magnesium. So this is our balanced chemical cell that's happening here. Just looking at this, I can see that iron goes from 0 to plus 2, so that would be our anode, and the magnesium goes from plus 2 to magnesium, just the elemental form, so that would be 0, so that's our cathode. So let's go back to the table and see, is our anode, which is the iron, because it's being oxidized, is the iron lower on the table than the magnesium? Let's find those. So there is iron, but it's not the right iron. This is iron 3 plus. We want iron 2 plus. Iron 2 plus is right there. Okay. So is our iron lower on the table than magnesium? It is not. Magnesium is lower. Magnesium going to magnesium 2 plus is lower on the table than iron. So what that tells us is that this reaction is not spontaneous as written. The spontaneous version of this will be the opposite direction. So essentially these two will be our reactants, and these will be our products. So we will have Fe2 plus magnesium going to iron plus magnesium 2 plus. That is the spontaneous version of that reaction. And so if we're going to sketch that really quickly here, you just call me Vincent van Gogh, or Bob Ross. Actually, call me Bob Ross. My mad art skills here. So we were told to put the anode on the left. So we're going to have the magnesium on the left and the iron on the right. So this stick here, this chunk of stuff, that is actually magnesium metal. This is iron. And then in solution, we will have magnesium 2+ and iron 2+. And so the other thing that they told us to be sure to label was the direction of electron flow. By the way, in the middle here, we just have something that's using the power. It doesn't really need to be a specific thing, just something's there. Electrons are always going to flow from the anode to the cathode. So again, this is the cathode, this is the anode. And that would be labeled on your battery. The cathode is the plus side, and the anode is the minus side of the cell. So then for the other one, we have iron again. So it's the same half reaction we had in the first one, so we don't have to look for that one. But we have lead instead of magnesium. So lead 2+ going to lead. If we go back here and check for that, lead is here. Lead going to lead 2+. So now the iron is lower on the table. And the iron was still written to be the anode in that chemical reaction. So because the anode is now lower than the cathode, this is indeed the spontaneous direction for this reaction. And so we can just sketch this as it's written there. So it's going to be just the same thing here again. We have our salt bridge. We have our stick of iron on the left now, since it is the anode. Over here, we're going to have our stick of lead. They are connected, powering something there in the middle. We have our liquid in there, our solution. There is some iron 2+ floating around, and some lead 2+ floating around in here. Again, this is our anode. This is our cathode. And electrons are always going to flow from the anode to the cathode in a spontaneous cell, anyway. If your reaction is spontaneous, the electrons will go from the anode to the cathode. And since I am Bob Ross for today, here's a nice happy little tree for you. I've got a happy little tree and his cloud friend. They're enjoying watching this this electrochemical cell. So there you go. All right, I think we'll stop there for this video. Nice video of example problems. We're going to pick up in the next one there talking about how the cell potential relates to the stuff that we've been talking about for the last few chapters, how it relates to the Gibbs free energy, how it relates to the equilibrium constant. So I will see you all in the next one.